And, you know, I tell the speakers, we have to have some discipline. We have to, you know, make fairly concise statements and not, you know, start to give it seminars. But I trust them. And because I want to have some time for discussions between the members and discussions with you. So if you want to have, you know, ask a question, think about it, and then with luck, we will have time for that. So what I would like immediately turn here, and I ask Carlo.
Oh, no. I'll be the last one. Go ahead.
Well, the question is, how do you see the future of fundamental physics?
Well, I said a bit about that in my talk. I won't repeat most of it. I am an optimist, always. So the future is wonderful and bright and optimistic in physics. I think I see no problem in experimental high-energy physics over, say, the next 50 years. We will build a successor to the LHC somewhere. It's nice that there are wonderful alternatives and plans being, and I think by and large we should support as many as is possible. I especially look forward to Asia beginning to contribute in a significant way. It's a large part of the world's economy and can afford to. Japan, of course, and now China, India. In theoretical fundamental physics, I have enormous hopes because we are beginning to have extremely well-defined questions about the unification of the forces of nature, the nature of space-time, the quantum properties of space-time, the history of the universe, the beginning of the universe. These questions are getting to the point where I am convinced that they will be answered this century and probably in the first part of the century. Of course, in the longer run, high-energy physics does, in high-energy physics, there is an ultimate, there might very well be a serious problems in continuing to follow Rutherford and try to learn about the basic structure of matter and force by smashing particles together. And I applaud Carlo for pursuing new ideas in smashing particles together, but maybe even new non-Rutherfordian techniques will be required in the 22nd century.
Why don't you,
I pass it down.
Yeah, I written down a big statement, but I'll try to take some points out of it. I will limit myself to fundamental theory and the future of that. There are still many things to be done, particularly by physicists who are ready to disobey the authorities. Like in the past when we disobeyed the authorities who said that quantum field theory would never work, or that internal symmetries can never be mixed with space-time symmetries. You just ignore all those statements and do it anyway. So I think the present state of our understanding of quantum gravity is very unsatisfactory, to say the least. Even superstring, or if you will, loop quantum gravity, all these things, they still need all sorts of major corrections. And my complaint about these things is always that we do not understand nature's bookkeeping system. We can't even formulate the degrees of freedom that we have to deal with when we try to quantize gravity, and how a cutoff has to be introduced in order to avoid infinities there. I'm convinced that nature's bookkeeping system can be understood by using black holes as guidelines. Black holes are marvelous objects. We know they should obey some reasonable laws of physics by themselves. Whereas if we try to deduce those, we get unreasonable laws of physics. There's something wrong with our understanding. I think that the chain of arguments that led to superstring theory has some very weak points, weak links, in particular at the very beginning. And now I'm getting aware of the idea that superstring theory, as it is introduced, is usually introduced as an analogy, well, as something that has to be applied first in QCD, and then you just transport it like an old detective from Daisy. You just take some abandoned theory and then you use it again in quantum gravity. It's not going to work that way. I think the foundations of superstring theory are extremely weak. So is it unscientific to discuss such foundations? I would disagree with that. It is hard, however, to discuss them correctly. So there are gaps in 20th century science, and I think those gaps need to be repaired. And one of my complaints also about string theory and about the way we are dealing with things is all this load of conjectures and speculations that are involved. You make a conjecture, a speculation, then you assume all these things to be true, and then you go on. Whereas actually these conjectures and speculations are bridging much bigger gaps in our understanding than we should afford. We should inch our way forward, which is much more powerful than trying to make giant leaps. I'm sure that giant leaps in physics, theoretical physics, are not going to lead us anywhere. But okay, that's my personal attitude. And for the rest, of course, I agree with what David said that, about the tremendous chances that lie ahead of us and the tremendous problems that will be solved. I'm pretty sure of that.
Yeah, thank you. So we start with the sort of the theoretical side, and I really want to say that, as David said, that you have to be an optimist. I think we are having a wonderful future in theory, and all these pieces that were put together, they will be put together. I mean, the only thing I'm sort of feel sorry is that it takes longer time than we ever thought, and it's not clear that we will be around when we have solved it, when we have understood the basics of superstring theory. But this is something that we can continue to discuss, and you can think about questions or issues that you want to raise there. So let's now go over to the experimental side, and I don't know who will want to start. Would you like to start, Peter? You can use it.
Well, first of all, I'm also an optimist, and I think there's a bright future for particle physics, but we have to work hard for it. It will not come from alone. And first of all, let us not forget, well, Lars, you said 10, 20, 50 years. So 10, 20 years, clearly the backbone is the LHC, and I think we should not forget to exploit this fantastic instrument, these fantastic detectors to do that. But let me also warn you that it will not come from alone. There will be a big effort needed. Now, I also believe that there are physics questions which will require higher energies. And, well, just thinking back how long it took to build LHC, I think it is the right time to prepare options, what we will do in the future. And clearly, well, it's, I think, not a surprise to you that I am rather enthusiastic to develop the concepts of a very large hadron collider, to develop the technologies, to develop the instruments for that. This will take a lot of time. I think natural time scale also to develop these ideas is, well, seeing from the European side, is the next European strategy of particle physics, which will be 2019. So that's the time scale where we should be much more concrete what is to our disposal. And I think naturally one of the expertise which CERN has is hadron colliders, high field magnets. That's something which should be developed. They can also be used at other places in the world. I don't say this all has to be done at CERN, but certainly CERN will play a role in these developments. So for the moment, that's what I want to say.
Okay, and I would like to say to all the young people here that if you ever have a chance to visit CERN, to work there for some time, you should go there, because it's the most remarkable organization. I think it's one of the real successes of mankind, to be able to put so many people together, work so hard and so successfully, and you have some of the pillars that CERN has been built on here, and for a theorist coming down there, it's always amazing. How can these things work? You have these millions of cables. How do you know that they are connected correct? I never understood that, and so you have to go there and see it. So Jim, will you continue? Okay. You can even take that.
I think let me start by echoing what Peter has just said. I think one of the things that which strikes me is that we're 10 years late in finishing the work of the last century. So in a sense, the physics of the last century, which constructed the standard model, as I said earlier in my talk, is a towering intellectual achievement of mankind. And in that sense, what are the steps coming up? How do we see the future? Also, as has been alluded all through this 2 days, there is physics to be expected beyond the standard model, and there is experimental evidence for it. We don't have to rely necessarily on our theorist friends to tell us that, although they do tell us what sort of things we'd be looking for. So in a sense, I think Carlo mentioned that it's a good moment to be an experimentalist, because I think the answers of which way we've got to go to, which direction we've got to point to, are going to come from the experiments. They're going to come from possibly a wide range of experiments, because we don't know what the answer is. So they can come from the LHC, they can come from neutrino experiments, they can come from dark matter searches, and all sorts of wide range of experiments. So I think what's ahead of us is a broad front which has to be attacked. And from there, we might actually find the clues that should tell us what we have to do. Now, it's also true that we've just increased the energy of the LHC to 13 TeV, and we have to expect to see something, hopefully. And one point to note is that to actually see what is happening at 13 TeV will take a few years of data taking and analysis. So when we make our choices, we have to bear that in mind, that there will be clues there which we then also have to use in making a call wherever we are in a few years' time. So in that time, we should actually prepare, as Peter has just said, options. If you don't have any options, you don't have any choices. But if you have options, then you can exercise the option in light of the data that you've got at the time that you have to exercise that option. And in creating these options, you have to worry about three things. You have to worry about the accelerators, you have to worry about the detectors, you have to worry about theoretical input as well, and theoretical work in terms of actually exploiting the results that you see. Calculations, the precision of calculations, and for example, we talked about Higgs couplings. Actually, we can have large amounts of data, but can we actually confront the theory with it? So that requires that. In accelerators, it's clear that there is the high energy part, which is what Peter alluded to. But there are other things as well, in a sense that I think Carlo has mentioned. So in terms of accelerators, as far as Z plus, Z minus is concerned, you have to have accelerating technologies which are very efficient and cost effective. In the case of the Large Hadron Colliders, you have to have very powerful magnets. So you've got to do actually the R&D now on the magnets, to have the magnets which have about 1620 Tesla ready for the time when you have to make a decision. And similarly, I think Carlo has mentioned this issue of cooling, muon cooling. Muon, actually, high-intensity muons opens up quite a broad front of physics. And the first step is actually to do this cooling experiment that Carlo. So in that sense, that's a prototyping R&D, which Carlo's mentioning as a scale is not terribly high, comparatively speaking. So that's the sort of preparation that one needs to do, in fact, and to prepare these options. And the other thing which I wanted to say about the LHC as well is that the lifetime of an accelerator or an experiment is related to 3 or 4 objects. One is that you increase the energy, the other is you increase the integrated luminosity. Third is you improve the detectors. Fourth, which is also quite important, is that you have to keep the doubling time short. So we can't actually spend 5 years to double the data set. Then it doesn't make sense. So that actually also means the step that we've got to take in increasing the instantaneous luminosity is necessary. But at some point that will also have to finish, and we have to be ready to actually build a new instrument at that time, and it's not far away. And the timescales, as we mentioned, are long, so we have to prepare ourselves, prepare the options, and as Peter mentioned, at some point we'll have to put them on the table and then make a call. So I'll stop here.
Okay. So, of course, you know, what we see now, you know, in the development of physics is that it's spreading so much, it's broadening the whole world, and we can thank, you know, for example, ICTP for bringing in the whole world into fundamental physics. And this part of the world that we are now is, of course, a very important. It's, you know, it's becoming richer and richer, and more sophisticated. And of course, the first country that started to become very sophisticated, very rich, is Japan. And Japan has a long tradition, first of doing theory, very good theory, and then also building accelerators. So, of course, Japan is a key player in this game, and it's interesting to hear what you have told us a bit about it today, but what would you tell here about the future of fundamental physics, say, from a Japanese point of view?
Before going to that, since I'm a theorist, maybe I should make a brief comment about the future of theory. I was very impressed by the talk by Professor West yesterday. I believe that's the direction of the future of string theory. Well, the basic idea is to formulate the framework in terms of algebra. Physical system is not defined by what we call Lagrangian. It's defined by algebra. It's very much in conformity with the modern mathematics. In that, in his formalism, string or any other branes come in an equals stance. And in that way, string neither branes a fundamental object. I was so excited about his talk. Thank you very much. That's all I wanted to make a comment about it. In that formalism, I don't know how you define moduli, for example. There must be many, many problems remaining, but nevertheless, I was very delighted. And that was the idea I had since my postdoc days. Now, coming back to this issue of Japanese concept of future of our community. I must concentrate on the experimental side. And for that, I would like to show a few transparencies, a few PPT, which I failed to show in my 45 minutes talk. That is, how, would you like to help me? Oh, I just put it. Okay. David Gross mentioned a very important role of Asia in future. And of course, Japan is one of the countries in Asia, but also China. And I want to compare the Chinese or CERN Hadron Collider with SSC. It's many of you are theorists, so it's just a fundamental parameter I want to compare. Okay, new proposal is the energy of 71.2 TeV. SSC was 40 TeV. Circumference, new Chinese proposal is 54.4 kilometers. SSC was 83 kilometers. All these are not much different. No. Dipole field, because of a small circumference and larger energy compared to SSC, it's 20 Tesla compared to SSC's 6.6 Tesla. And there is some factor of 100 difference in the luminosity. I want to just concentrate on this 20 Tesla dipole. You just remember this number. And I want to go over, because I have a time limit. Let me compare now ILC with Chinese or CERN proposal of a circular electron machine. Now, the proposed circular machine is around 200 GeV, which is not very much from the 207 GeV LEP machine. Therefore, not much technical issue existent. But the problem between the ILC and the circular machine is the consumption of energy. Now, 240 GeV machine consumes 500 megawatt, while ILC with 500 GeV consumes 160 megawatt. Being serious, maybe you don't know much about the 500 megawatt mean, but most of the big power generators, oil or nuclear, is about 1 gigawatt. So you have to consume half of the regular reactor just for this machine. And because of synchronous radiation goes e to the fourth, it's almost impossible to go beyond this energy in the circular machine. You need several gigawatt generators to operate this. Now, physics-wise, I show you in my 45 minutes talk that it's very important to understand phi to the fourth or self-interaction of Higgs. And I showed you that to study this, we need very, very precise Topcock mass. And to do that, you cannot stay in 240 GB. You have to go at least up to 350 GB. At the moment, I will stop here, and I want to make some recommendation later, friendly recommendation to our Chinese friend, and also to foreign friends.
Well, thank you for the moment. So now we have some of the cards on the table here. So perhaps it's time now, Carlo, that you tell me.
Okay, well, I tried to summarize a few things. After these interesting questions, many other people already developed. I don't want to repeat myself. However, I'd like to say a few things. First of all, I would like to say that to the theorist, of course, is a part of the mind. It can be developed freely. But the experiments, they should not forget that we are doing natural philosophy. And natural philosophy is not determined by the ideas or the comments or the thinking of people. It's based by nature. And therefore, I think the experiment, as you pointed out, experimental physics is the fundamental thing which is behind our field, and that is the one which is determining in the long run, at the end, what is right, what is wrong about what's going to happen. Now, in the experimental physics, there is a major new change coming up. 50 years ago, you were doing experiments with a single individual, bringing maybe a couple of graduate students or technicians and a person, and 10 people was a large number of people. Today, we are witnessing with the presentation we had this morning, beautiful presentations, 3,000 people working on one subject and 3,000 people working on another object. And therefore, under those circumstances, there is a major change in the way in which the physics is being run, because if these several thousand people, which, by the way, are part of a structure which is very well organized, very well differentiated. Every one of these people is now doing one part of the work. Now, for the first time, we are in a situation in which there is not a single individual which can put together all the elements which are characteristic of one of these major experiments. It takes different people which have different competencies, and only by putting them all together that you get some plus. While this was not the case at the time in which we are doing more traditional physics, in which you had only a small group of people working on this. When it comes to the future, of course, it's perfectly obvious that we need to go to higher energies, because that's a way in which you can see progress to develop things, whether they are electrons or whether there are protons or whether there are muons. This is something we can decide, is a technical point. However, it remains that there are fundamental limits which are coming up, which are additional limits which are coming from the nature of the physics itself. Namely, we have, for instance, the fact that when you go up in energy, the cross-section goes down like a square of the energy, which means that 10 to the 32 was a perfectly, second minus 1 was a perfectly solution for LEP. 10 to the 34 is what LHC is now going to do. And tomorrow, if you're going to go another big factor, you mentioned here the example, the 74 GB machines or a super SSC device, then you'll have to go down to 10 to 36, 10 to 38. And there will be, out of this, not only a limit coming from the availability of funds or the resources, etc. There will be a fundamental limit coming to the fact that the cross-section becomes so small compared to the other system that there are fundamental limits that you cannot resolve. So there will be a limit, not too far from her, where the cross-section will get so tiny, so small, that it will be extremely difficult for a person to be able to collect sufficient number of data. And so this kind of limit is really coming up quite close. And this has to be very carefully evaluated for a future program. Now, of course, we have one advantage with us. We have a globalization. Globalization means that now today there is not a single experiment of some value which does not have a worldwide access. And in a certain sense, that makes the place where you do it relatively unimportant compared to the type of choices you're making and the people which can do it. You have to get the best people of town, getting together, working all together, and producing the system. Let me stop here because the time is up.
So as a theorist, I must say I'm a little disturbed by my experimental friends in the sense that I would like to see a world, say, in 2050, where we have, as an example, say, a PP collider outside of Beijing, a linear collider in Japan, a muon collider in Geneva, or some variant of that. And I find it disturbing that we aren't working on all fronts simultaneously. Now, clearly, there are scarce resources, but the way we are going to make sure there are scarce resources is starting to fight among ourselves and compare a imaginary design, for example, for the Chinese diameter of the SBCC, which is not yet determined, and make such comparisons. It will not serve our purpose to hurt the ability to get what is soon to be the largest economy in the world to contribute its share of fundamental science. And it will also not help our activities to imagine that all of the answers lie in Geneva. You still refer to CERN as the European machine. You have not, Israel is now part of Europe? I thought you were already a world machine. But it's still a European machine. You talk that way, and yet gave me the assumption that Europe is the place where important decisions will be made in 2019. That might be true for the next 20 years, for sure. But there are other possibilities around the world which need support, at least words and help and collaboration, if not money. And so I think we should stop fighting or trying to exert hegemony. I can speak this as a third world country coming, which has no aspirations to hegemony anymore.
Who's fighting?
Well,
I don't understand. Where do you see the word fight? I don't know.
No one is fighting. That's great.
Okay.
It's fine. Then I don't want to talk.
No, and we are really talking about globalization here, and so I think we should come back to these things. We still have one contribution here that we haven't heard, also coming from Asia. So we will hear some other input from the Asians. Please.
Yeah. Well, first, thank you, Professor Esirkepov, for the invitation. I feel tremendously honored to speak here. Now, talking about the future of fundamental physics, and as a cosmologist, I would like to pitch in with a somewhat kind of tangential idea, not along the line of accelerators, but hopefully equally important. And since I wasn't scheduled to give a separate talk, so Lars kindly gave me some slight extra time. I hope you bear with me, and I thank you for your patience. But for that, I would really need to show you a few slides, if you allow me. Thanks. Okay, I'll try my best to be fast. So here I wish to propose a rather concrete idea to accelerate what I call the plasma mirror to investigate the black hole information loss paradox. Let me see how I can forward this. Yes. Now, we all know that black hole is a solution of Einstein's GR. And planetary, stellar size and supermassive black holes have been observed in space. So experts believe that they exist. but we can argue about that. Now, it is also well known that in 1974, Stephen Hawking made this seminal discovery that black hole is not entirely black, but glowed with a black body radiation whose temperature connects quantum mechanics, symbolized by the Planck constant, general relativity, where there's the Newton's constant, black hole mass, and Boltzmann's constant. So it connects GR, quantum mechanics, and statistical mechanics in one stroke. However, the nature of it, after 40 years, is still somewhat at large. Very soon after his seminal discovery, Hawking recognizes in 1978 that the black hole evaporation may result in the loss of information. And this points to a very important potential conflict between general relativity and quantum field theory. And I am actually, this small presentation here is strongly echoing what Professor Tufts just now commented about the importance of black hole physics as a window peeking into the quantum gravity, although this is still in the semi-classical level. But this reminds us of the study of quantum field theory, QED, before World War II, where the famous renormalization was not yet discovered, but we go ahead and study it into, say, Compton effect, Bethe-Heitler effect, nonetheless. Now, in the past 40 years, there's endless debate over the nature of this black hole evaporation, and with tons of solutions, including, for example, the black hole complementarity, and the recent suggestion about the firewalls, which has been hotly discussed over the last 3 years or so. And there's also the idea first raised by Frank Wilczek in '87, the entanglement between the Hawking radiation and their partner particles. I'll come more into this a little later. And there's also the idea of Planck-sized black hole remnants as a shelter for the Einstein-Rosen bridge type of tunneling, or the savior of the missing information, etc. There's also the idea of naked firewalls, just recently suggested by Don Page, Sasaki, and myself, and several collaborators. The most recent, as you probably saw from the news, was this so-called soft hair proposed by Hawking, Perry, and Strominger. So there's no lack of ideas. However, I would say that the ideas are essentially all in the theoretical domain, which is not so surprising because astrophysical stellar size or supermassive black holes are just simply too cold and too young in the sense of page time. So there's no much way to study this information loss paradox. Now, so as Carlo just now was emphasizing, physics is fundamentally an experimental science, and we wish that we have a way to investigate these issues experimentally. Now, in short of a direct observation of these effects from space, there's been the idea of analog black holes. And over time, there's been various proposals, suggestions, and myself involved included. Now, but these is basically the test of the black body thermal nature of Hawking effect, not much to do with the information loss issue. Now, since time is rather short, I will just skip these 2 pages, but you probably know already that in the investigation of the nature of Hawking radiation, Unruh came up with the recognition that an accelerating observer would see itself embedded in a thermal heat bath in the vacuum, which also has a temperature that goes extremely similar to the original Hawking temperature, with the acceleration at the event horizon replaced by its proper acceleration. Now, this was suggested to be testable by establishing a standing wave linearly polarized laser and put your test particle, in this case electron, at the antinode where there's only the electron undergo violent accelerations. And so this is just one example, but it's not what I'm suggesting today. Now, for those of you who are not too familiar with laser technology, it has been undergoing tremendous progress in the last several decades. And just to say something which you may recognize, appreciate better, at the level of 10 to the 30 watts per centimeter square, the field is so strong that the electric field energy per competence wavelength is about 1 MeV, where vacuum can become unstable and Schwinger tunnel. And so vacuum, you can say, is becoming boiling. Now, but current technology is already pointing towards that direction. But that's just to let you know that aside from accelerators, laser technology has been undergoing tremendous progress. Now, the plasma...
Sorry, you're 5 orders of magnitude less?
Right, I don't need that. I'm just pointing to you as a reference. So now, some of you might have heard this idea called plasma wakefield acceleration, originally suggested in 1979 to use laser to excite the plasmas behind it. Now, in 1985, my collaborators and I suggested that particle beams can, replacing the laser, can do the same job and can drive even longer distance. Now, in the nonlinear regime of such beam plasma interaction, the plasmas are perturbed so much that its density perturbation is accumulated behind it like a delta function. Now, there's what I call the wakefield principle. That is, the group velocity of the driver, either a laser or a beam, is equal to the phase velocity of this wake behind it. And let's try to remember that. So now, sorry. The principle of this, which is not unrelated to what we were discussing just now about the future of high-energy physics, has been demonstrated as like with the electron beam driven, at LBL with laser driven, and the acceleration of the gain of the order 100 GeV per meter has been observed. Now, currently there is an ongoing experiment by the acronym AWAKE carrying out at CERN, following this particle beam driven idea. So this is a rather active field in physics currently. Now in 2003, it was suggested that this very delta function-like plasma wake can serve yet another really nice utility. Namely, so this is a driving laser which drives and excites some delta function wakes behind it. With the proper tailoring of the transverse profile, one can make this delta function plasma wake as a mirror, where a witness laser pulse can be reflected and Lorentz-boosted to a higher energy and therefore shorter wavelength and therefore better focused to reach an even higher peak power, peak intensity. Now, so here's, so what can this plasma do? Now, the nature of this plasma wake, just by conservation of energy, this guy is going to slow down by dumping energy into the plasma to create these mirrors. However, there's a way to make it accelerate. If you send this plasma, this drive beam, this laser, into a plasma which is pre-tailored with an increasing density, then you are able to, then in a non-uniform plasma, it can be proved that the dispersion relation now is slightly more complicated with an extra term which has to do with the plasma density gradient. All you have to do is, if this term is positive, then your denominators get smaller, your group velocity and therefore also the wake phase velocity is increasing. So this is our idea. So now these days, nano-fabrication is already down to the atomic level. So imagine that you can fabricate a solid target with a density exponentially increased from front end to the back end. Then you will find that your plasma wake, the laser pulse itself and therefore also the wake field, can accelerate. Not only with a constant acceleration, but is with a non-vanishing third derivative, which is necessary if you want to test the black hole physics. So here's a small example, but let me skip the details. What it is suggesting is that, and this was first suggested by Frank Wilczek, that an accelerating mirror in this space-time diagram starts from rest, rapidly accelerates, and all of a sudden at the back end stops. So the question at stake is the following. For every Hawking particle in blue that is reflected by this plasma mirror, there's always a partner mode in the vacuum fluctuations, which just flies along the equivalent event horizon here. This is the future null ray. And suddenly, this mirror stops. So there's supposedly an accumulation of a lot of these partner particles, and that would turn out like a burst. But there's the suggestion that actually the vacuum is not going to have that because they're indistinguishable from the real vacuum. So these are one of the key issues that can be studied with this plasma mirror accelerating. So sorry to take you so much time, and I'll stop here. Thanks.
No, thank you. I think it's important also that we think about all possibilities, how we can proceed, and all all new methods are interesting, and that they have to be tested and they have to be compared, and that's the same with all these. We have now very nice examples or suggestions of new accelerators. They have to be compared, but hopefully, as David says, they can be, discussed in parallel. And we have now gotten into this discussion about what the Chinese physicists can do, and there are suggestions. And unfortunately, we don't have any representative from China here, but we know that they are very interested in hearing what these experts here say, and that's so. I think I should come back to you, Peter. Now, in the what you've heard here, how do you see say the comparison between you would try to build a huge accelerator around the whole of Lac Le Mans or something to be compared to having a global effort, say, in China? What are the advantages? What are the disadvantages?
I'd like to make a small comment on this. I said that just to remind you that Enrico Fermi in the 50s had calculated the expansion of accelerators in the world, and they realized that according to the scenario, the latest accelerator will be around the Earth as such. It seems to me that we're getting a little bit into a situation which is going a little bit out of control. And the other question I'd like to mention is any new accelerator, any new development will start small, because you have just to make 1 meter of that. It will be a major head forward, which is completely different and independent with the idea of building up a big device, which, by the way, has to have a luminosity. We said next machine will be 10 to the 36, 10 to the 37. So, and there will be all these kind of questions associated with it. You cannot, you have to have positrons and electrons. In your plasma here, you're not using positrons, you're using electrons.
No, you can do both.
You can also do proton, but it's a second order approximation, and so forth and so on. It seems to me that it's very nice to dream, but the realities of everyday's life of a physics program are substantially different, and I think we should come down with the feet on the floor and realize what the real next step is, because that's the purpose of the meeting we have today.
May I just quickly respond? Yeah. So I agree that I'm once upon a time during my career I studied accelerators, and I spent some time studying muon colliders as well. So I'm very much for the immediate goals, and for these kind of crazy ideas, we're talking about farther future. And so on the technical side, may I correct that positrons can be accelerated by the wake as well, because in the linear regime, the wake just oscillates sinusoidally very much like in the vacuum tube. And there are different phases where positrons can be accelerated as well as electrons at different phases.
Okay. No, I think Peter.
Well,
Excuse me, let me just answer directly your question. I've been working myself. First of all, at CERN we have a wakefield program, which is a very sensible one. It's going to be in the associated with the CERN SPS, and we are going to do something very important. So there is a group of people working on it. I've been personally working on this field for the last 25 years, and it seems to me that the progress has been extremely slow from the way, because inventing a new technology of this type is not something you can do overnight. So therefore, this is a totally different story in respect to what we are going to do in order to ensure the high energy physics and the community of energy physics will get the proper response to their questions.
Yes, but coming back to your story about Fermi's concern.
It's a joke.
Not entirely a joke. I think although this plasma idea may not satisfy us to provide us the immediate next generation machine, the potential is so high, which can shrink a kilometer accelerator into 1 meter. I think it's worthy of putting in some investment into that.
Sure, it is
Yeah.
there. It is there.
That's right, yeah. And I also mentioned
How
that there
much?
is indeed.
Excuse me. CERN program for developing new things in accelerators is very substantial. I mean, for instance, CLIC has got 100 millions. All these other activities of Euro, and so forth and so on.
Okay. Yeah. Okay. Good. This is what the panel is.
There is a problem here, which and it is that new technology at high energy physics labs is supported meagerly. And you have exactly this problem now, Carlo, with muon, trying to get support for proving or disproving or exploring muon coolers, right? And Wakefield, again, is in exactly the same situation. There's a small amount of money being, so in the there was a big advance about 8 years ago in the US. Why? Because the recession happened and the US government decided to DOE, they gave DOE extra money if you could go out and find something which you could spend the money very fast to stimulate the economy. And the Wakefield experiments were ready to go, except they had no money. We're talking about $10 to $20 million, and they did marvelous advances. Now, then economy got better, the money stopped. And that's the fate of things that aren't in the traditional critical path survival line of major high energy facilities everywhere in the world, unfortunately. And that's why you are so far unable to do your demonstration, Carlo.
I'm 2 years old. That's why I'm not doing the demonstration.
Well, the muons have suffered from that, and the Wakefield plasma acceleration has suffered from that, as well as who knows what other ideas are suffering, because it is really true that the large facilities are conservative, and they're mostly concerned with survival, and are strapped for funds in general. So there's a tendency not to invest, in my opinion, sufficiently with new ideas, which, as Carlo pointed out, in 50 years are going to be crucial. Unless one comes up with some new, something beyond the current ideas on electron-positron colliders or proton colliders, in 50 years, the successor to the LHC, we're going to be in trouble. We better start thinking about that already.
Yeah, not only the resources are meager, the time is also meager. So we have to concentrate now to the discussion more onto future accelerators. It's very nice that we have these programs and the other programs. They should be continued, and someone will have a brilliant idea one day and we will see something else. But let's now go to the accelerators. And first, Peter.
Well, first of all, I would like to assure David there is no question of fighting. As I said, there are technological issues which have to be developed, which are independent of where it is. But like the high field magnet, but you have to do them somewhere, and I think, well, this has to, the dream is that it's developed globally, and there is a fact, I said CERN has some expertise in that, and CERN is certainly open to have this as a global development. There is another issue which clearly has to be addressed from the side of the experiments that Carlo pointed out correctly. We have to be able to operate at high yet an order or more magnitude in luminosity, the detectors. So this means for sure going, I think, to 5 nanosecond bunch spacing and things like that. Otherwise, we will not be able to deal with that. This has to be developed independent from where it is done in the world, if ever. So,
one other point, if you don't mind, to add on this limitation for the next step, which supposedly is to be high energy. If we go hadron, if we decide that we want to go to a much higher luminosity, make an example, SSC as an example was given as a reference case, we have to realize that the magnetic forces are becoming very large. Let me remind you that the first large superconducting ring was a tevatron at Fermilab. Bob Wilson developed it, and that was a 4 Tesla affair. Then now we had an 8 Tesla affair, which is the LHC, which is already a very substantial step forward in the forces. And remember, the forces go like a square of the field, and so forth. And now we are talking about something to go to 20 Tesla. At 20 Tesla, you get something like 400 times the force that you get at 1 Tesla. Now, at 1 Tesla, you get a force which is of the order of several atmospheres. 4 or 5 atmospheres. So we are talking about forces of 2,000 bar atmospheres pushing in a very irregular way, not a solenoid, which is easy to make, but a dipole, which has the forces coming in, coming out, and so forth and so on. So it is quite clear that our limitation will be at a certain moment, they will start cracking the metal. The metal will start bending, because from 8 to 20, it's a factor 2.5 squared, which is almost a factor 10 in the rate of the forces. So we have to be very careful that if we go conventional, the solution to a very high field is not an alternative to make a very large machine. It's much easier today to build a machine, I assume 10 Tesla or 12 Tesla, which still will be another factor 2 or 3 in respect to LHC, and make it substantially larger rather than going to compressing a machine like that in a small scale. Also because maybe one day people will learn how to go to higher fields, but the other question, the question of luminosities, is also a question which you'll have to worry about.
well,
So there are fundamental limits. Independently of money, independently of there are limits in the way in which you build accelerators, which you'll have to face sooner or later. And we are very close to that. By the way, let me tell you, this was something which was pointed out many years ago by Leon Lederman. Leon Lederman made a long story about, I remember once we were discussing this, pointing out that the limit of the high energy collider will be the field and the cross-section, the luminosity.
Well, first of all, let me say I have not talked about 20 Tesla. Yeah, it's 16 Tesla. What? Yeah, but okay.
I lost
Now, Carlo, also, I think you're right that one has to go in steps. So the next step is, in fact, on the LHC upgrade to make the quadrupoles with niobium tin to go to some 12 or so Tesla. And, okay, that will give the first experience with this type of magnet.
May I? Yes. I never disagree that muon colliders or the plasma accelerations are not important. It's a future accelerator, and ICFA always pushed the research activity in this area. But we are now in the stage of a concrete proposal from China and also from CERN as the next generation of accelerators. So I want to concentrate on this issue. And based on the unsuccessful effort of SSC, I don't want China to follow that process. It was unilaterally proposed, but it should be the worldwide effort, but initiative will be taken by China and also by CERN. That's why I want to make this friendly advice. 100 TeV hadron machine is more or less the consensus of the community. Maybe Professor Rubio is against this, but global effort towards 20 Tesla using niobium-3 tin superconductor magnets must be started as soon as possible to finish the work in 10 years. It will be very hard for only China to go ahead and finish it in 10 years. So it must be done in global collaboration. Beijing and CERN should take the initiative under the supervision of ICFA. US, Japan, other countries must be involved. Test stands must be constructed in IHEP, China, CERN, Fermilab, KK, or any other interested laboratories in the whole world. I want to emphasize that going from 13 Tesla, that's sort of quadruple magnet for the insertion for high luminosity LHC. 16 Tesla to 20 Tesla is not increasingly, is an increasingly stupid uphill process. That's why we think we need worldwide collaboration. Next, about E plus E minus collider, I advise ICFA to form an international panel, like what we did for linear collider technology, the selection committee, to discuss whether it is a good idea to have a lepton machine before going to the 100 TeV hadron machine. The panel must be composed of theorists, experimentalists, and accelerator physicists, as in ITRP. My personal opinion is that I'm afraid that 240 GB E plus E minus circular machine may not be productive enough in physics, because I pointed out that 350 to study top quark mass is necessary, must, to understand the Higgs potential. But I'm afraid going to 240 GB E plus E minus before 100 TeV machine may just simply delay the construction of 100 TeV hadron machine, which nobody wants.
Okay,
So this is my proposal.
Okay, so Carlo.
Can I make a comment on this? I would like to, well, first of all, let me tell you that this idea to make this 100 TeV machine was already proposed 20 years ago by Antonino Zichichi. And he was called it Eloisotron, as you remember. And that object was supposed to be in Sicily. It covered whole Sicily around, as you remember, in a picture. So this thing seemed to be coming up several times in a variety of different ways. So I'd like to underline such a point. Okay.
Yeah, Jim, you have...
I think the point I wanted to make, and I made earlier, is that we have to wait for the LHC results, because if you find an object, it's likely to be heavy now, because the lighter ones we would have found. And that does actually alter the dynamics from a few years ago as to what we should do. Because a heavy object, if we do find it, will be very suggestive that there are other heavy objects higher up. So, and I think now the point was to put things on the table in terms of the design studies. And when the moment is when the results from the LHC come in, which is this run 2 probably, which is in 3 years' time, or 2.5, 3 years' time. But the other point I wanted to stress was the creation of options, and that I think doesn't mean to say where the object finally is situated.
Sorry. When it comes to your objection, you said you want the whole thing in 10 years. Apart the money, the size, the dimensions, everything else, there's one other question. You probably know that every one of the accelerators, for instance, let's take a case of CERN. CERN has the LHC, but LHC is fed by the SPS. The SPS is fed by the PS. The PS is fed by the booster, and the booster is fed by the LINAC. In other words, if you want to build a very huge machine of this magnitude, you have to construct a complete series of satellites of other machines, which are coming from particle at rest, all the way up to an energy which is sufficient to be accelerated at these very high energies. Now that requires a whole chain of accelerators which exist after many tens of 50 years of development in Fermilab. There are at Brookhaven. There are a little bit in Japan, although Japan is a much more modest program, and there are also at CERN. So to go into a virgin place like China, it says in 10 years, I will not only build a extraordinary machine, which is a beautiful thing, but I will make sure they have all the equipment which is required to feed that machine at the proper luminosity with a proper beam. It's something which requires a whole chain of new progress, because you cannot have a machine like this at CERN and send you a beam from CERN to China. You have to do it where the place is. So under those circumstances, the problem is much bigger than you think.
Unfortunately, there's nobody here to represent the China, just people discussing it or giving it friendly advice or unfriendly advice. But there is no plan to build a PP collider in 10 years. That's it. No, he didn't. He advised that. But of course, that's impossible. The Chinese plan is to build an electron-positron collider, 240 G, which so far one discovery has been made at LHC, extremely important for the Standard Model, okay, and for future experimental projects, the discovery of the Higgs, that defines what is a necessary energy and sufficient to some extent for an electron-positron collider to explore the Higgs sector.
You also need accelerator for the electron-positron colliders.
Yes, absolutely.
I mean, the SPS was also used to fill LEP. And without SPS, you would not have LEP.
It's not easy, Carlo. Therefore, what is your conclusion? That a country like China should not try to support elementary particle physics? Or they should start small and build BEPS and maybe a Z factory. You know, they should go slowly. That's your advice? Their plan, now trying to speak for the Chinese, which I'm in no position to do so, they have a reasonable plan and a reasonable time schedule, which starts with an electron-positron collider, which they have some experience, and then, and they do not plan to build, in my opinion, from what I know, a 54-kilometer tunnel. I don't know where you got that number from. That's the lower limit of the range that was still under discussion. Most likely, I predict, as a theorist, it will end up being 100 kilometers, which is what's needed, with lower field magnets. You know, the PP collider that is being discussed would already be in operation, we all know, if the SSC had not been killed. It would have run in 16 years ago at 40 TeV, way above the L8C energy, and it would by now probably be upgraded. So, you know, this is not impossible technology. Clearly, for a country that does not have these major facilities to begin to become a major player, there are two choices. One is you start slowly and you gradually build up, and the other is you try to build up rapidly to the frontier. And that's a choice which the Institute for High Energy Physics in China and the people working with them have made to try to go ambitiously forward. And I think it's conceivable with the help of the rest of us.
I think I wanted to make a comment again. And we're actually talking about two types of machines. One, which is the fact that you have found this object, and you need to study it in great detail, and that requires an energy which is not the TeV. And the second one is the machine which we roll into one because we say E plus E minus followed by PP in both sites. And I think that does confuse the issue because the two machines are quite different. And you can't, I don't think it's reasonable to put them into sequence. Do one first and then wait for the other one, because you've got to remove everything. That's, 40, 50-year program. So is it, and one, no, but that's what I'm coming to, actually. Exactly your point. The point is that, in fact, the tunnel is a simpler thing to dig, and it's not a major cost. So instead of actually saying that, perhaps there are two different machines which need to be built. I suspect.
Again, unfortunately, there's nobody here from China representing China. Yulu, but the Chinese proposal is to build a tunnel twice the diameter of the L8C tunnel, which can house both accelerators at the same time. That makes a lot of sense. They can build it for half of what it would cost, at least half of what it would cost. Start out with E plus E minus, which they have experience with, which is standard technology, which is not difficult.
I just say very briefly.
We're talking
First
here.
of all, I'm a condensed matter physicist, but I'm very much concerned with the discussion. And this issue is very hotly debated in China. There's no consensus now. I just want to emphasize. As far as I understand, the leadership has not approved the proposal of constructing.
Let me ask you, Lou, what do you think, as someone who is not in high energy physics?
Because I'm involved in this big facility, planning and designing things. And I think the majority of the committee feel that it is still out of reach of the Chinese economic and scientific expertise at the moment to build up just this 240 GeV electron-positron collider. No expertise, no financial power. Because the budget originally said was 30 billion Chinese yuan. Actually, people feel that it's at least a double, if not tripled. Then I think the real issue I want to ask as a condensed matter physicist to my high energy colleagues is a more important scientific issue. Is what is the really major scientific motivation to have really higher energy positron PP collider? Because for LHC, that was very clear. Higgs and possibly supersymmetry particles. Higgs has been confirmed. Now, if the higher energy things is only to build a Higgs factory, that's one issue. But the question, what will be the energy scale you estimate? You have the hope to have supersymmetry available, observable. If that you have more definite idea, that's much easier to convince the funding agency. You say, we don't know the scale, then I think it will be more difficult. The same I mean, would be also for China. I mean, it's not just to take the lead. I mean, what is the purpose of that? I mean, what is the scientific motivation for that? This is my question.
I recommend to you the CDR that was put out a year ago, is on the archive of the IHEP. It explains in great detail the scientific justification. There's no question that this is a way of probing the Higgs sector. The Higgs is a particle which looks like the minimal standard model Higgs, but that has only been tested to some degree. The Higgs is a portal into new physics. The Higgs couples to any fermion that acquires mass, so it's a way of detecting new particles. It's a great program. It's the justification for the ILC first stage, for sure.
Well,
So the physics program is undeniably exciting, and undeniably there are many critical measurements that can be performed there that will be hard to do at the LHC.
Well, I would like simply to add one point, that the cost of making the ring, it's a small fraction of the cost of the program. Let me tell you that I know the situation for the LEP, because I was director when the bill was paid. So I know exactly how much it was spent and how was it spent. It was of the order of 400 million euro for the whole installation of these of the civil engineering, while the cost of the LHC plus LEP is 3 or 4 billion for LEP and about 10 billion for LHC. So the cost of the building is nothing compared to the other activities which are around. So you shouldn't take that as a representative of the requirements of creating a new facility.
Following up on this, I mean, this is the point in a sense. The tunnel, like the LEP tunnel, should be looked at as an infrastructure for the life of the laboratory. And in a sense, the question I was asking is, can one not afford the two tunnels and do different things with it?
Yeah. Can I? Let me now stick out my neck what I really think what one could do, a scenario, which kind of a dream scenario, namely, I think it would be good to have a Higgs factory in Asia, in another region than Europe, because Europe will have the hands anyhow full with the LHC. Obviously, this should be a global project, like LHC is a global project with a lot of international participation. In fact, for example, the US is very strongly in developing these high field magnets, is part of it. And then one would have probably such a machine, a Higgs factory, in the 2030 running. To exploit it is a program of 10 years at least, such a machine. So, and that would then give a natural time scale to put, for example, in Geneva, a Large Hadron Collider of the order of 100 TeV with a large tunnel, which I think, again, realistically, this will be 2045 or so, not before. I don't think can be built and developed before.
You're telling us a joke.
So,
I mean, honestly, you are Swiss. You cannot tell me that they will build the ring around the Geneva Lake and had the approval of the Swiss community. I think you are completely wrong.
Oh, you have, yes, please.
Yeah. Since I sit on the left, I guess, from the audience side, and being rather radical here, I was thinking more on the farther future. And as we have just talked about, that we seem to be approaching some natural limit in terms of energy, in terms of luminosity, etc. So we talk a lot about energy versus the size of the tunnel, etc. But here, let me just comment on the issue of luminosity. I'd like to call the attention that the luminosity that we talked about so far in the past 50 years, 70 years, I like to call it the classical luminosity, meaning we're just collecting the number of particles from each side divided by its cross-sectional area. This is kind of a classical area where there's tons of empty space passing. Now, so one possibility to overcome this natural barrier would be to collide particles inside nanochannels, where there's the natural, through acceleration, there's the natural radiation damping. And imagine you're sending in the right, people who knows channeling effects. It's like a potential, and the radiation damping naturally damps the particle down to its ground state. So once I did some calculations, and I saw that there's a different regime of luminosity, which I call quantum luminosity because h-bar is involved, that particles colliding along the same honeycombs of channels can have a much better chance of overlapping each other. And so I'm just kind of pointing out that if you are willing to think more boldly, there are ways to overcome what we thought to be the natural limit.
Okay, thank you. So when we had a discussion here last year, I was saying that, I'm not the first one to say that, but the accelerators of the last century is like what the cathedrals were, 1,000 years ago. When they built these huge cathedrals, they increased the knowledge about mechanics, about building enormously, and this society benefited from it for many, many years. We also have seen that, building these accelerators have not only provided us with the Higgs particle and the W boson, it's provided us with so much of new technologies, so much of, not only technologies, in computing, we have World Wide Web, etc. And we have not really, we don't have time to discuss that, but I think that's an issue that also should be brought up, in this part of the world. If you if you start to construct these new accelerators, they need so much of new knowledge that the whole society will benefit from it, and that I think is an important aspect of bringing in very huge or very sophisticated accelerators to this part of the world. That's one of my points. I think you agree with that. And I think we should wrap up the discussion now because we are soon heading downtown. So let me try to see if I can summarize a little bit of what we have said here. I think that all people here are in favor of building, new great facilities. And I think we're all agreeing that some of them should be built in this part of the world. And perhaps there can be, even 2 great accelerators being built in this part of the world. But this should be global activities, which means that there must be a lot of activity between China, Japan, Europe, and United States. So I think that all these have to be, very global efforts. And, we also have to have a momentum in it. So it sounds a little bit as it's true that we don't know what will come out of LHC now, but we should not lose the momentum. And so I think and finally I think we should say that we should be optimistic. We should believe, that we have a beautiful future, both in theory and in experiments, and we have to work together and work hard, as everyone says, to do that. Any comments?
Yes, just one quick one. It's following David's comment that while we are pushing for this immediate next machine, some percentage of resource
Yes.
can be put into the longer, the investment.
No,
into
I
the
should have
longer
said
future
that.
R&D.
Yeah, I forgot to say. Of course, we should not be just, looking with one eye. We have to look around. We have to, and there will be, new ideas coming up. We are talking about, as we said, 10, 20, 50 years. There will be new ideas coming up. They have to be pushed. They have to be thought through. They have to be checked. One has to build smaller experimental facilities to test the ideas. And that means that also the society have to be open to these new things. We should not just concentrate all money in one box. Okay, I think that we have been sort of exciting. Unfortunately, we didn't ask the audience too much, but I hope you have at least got a feeling for how the discussions go, what are the plans. And you should remember, as a physicist, be an optimist.